everybody can see it. Yes. Okay. I'll try to talk something about our joint work with Nikhilesh. So this work is in progress, and I would like to discuss just part of this work, and maybe not only this work, but some basic facts in local and nilpotent derivations on polynomial rings. So let me say that K is algebraically closed field of characteristic 0. And let us consider polynomial ring in n variables. Okay, we can consider derivation of this ring. This is just linear operator which satisfies the Leibniz rule. Let us denote this derivation d, and dfg is equal to f dg plus g df. Okay, everybody knows, I think that all participants of our seminar knows that every derivation of this ring have the following form. f1 multiplied by partial derivation on x1 plus f2 multiplied by partial derivation x2 plus something fn multiplied by partial derivation on xn. Okay, but we would like to consider not only derivations, but local and nilpotent derivations. And the problem is to the problem is to understand which derivations of such form are locally nilpotent derivations. This is a very difficult task. So let us define some characteristic of this derivation. Let us say that rank of D is the minimal number of non-zero summands in this sum. I mean that we can change coordinates, and after this changing, the number of non-zero summands can be changed. Let me give an example. If I have derivation sum of two partial derivations on x and on y. This is a derivation of polynomial ring in two variables, and I can change coordinates. I can use another coordinates. K of xy is equal to k of uv, where u is x plus y and v is x minus y. Then, of course, we can check that this derivation d is equal to something like d du. Let me think. Yes, when we apply d to u, we have sorry, 2. We have 2, and when we apply d to v, we have 0. So rank of this derivation is 1, not 2. We have 2 summands, but in this form we have just 1 summand. So rank is the minimal possible number of summands. This definition can be restated in other way. Let us say that an element, let me denote by B all polynomial ring. And then I say.
And why do you have this 2 in this previous example?
What?
How does this coefficient 2, this color, appears?
I apply d to u, d from u. It's equal to 2.
Right. 1 plus 1. Okay, sorry, I see. Mm-hmm.
If I have an element y from this polynomial ring, then I can say that y is a variable or maybe coordinate. I will use notation variable. If they exist y2 and so on yn such that k of x1 such that b this b is equal to k of y2, so yn. Okay, so if this is right, maybe I shall put index 1 and here is y1. If this is so, I say that y1, y2, and so on, yn is a coordinate system. Or maybe system of variables. Okay, and another definition of rank is that rank of D is equal to n minus maximal maximal number of elements of system of variable such that they belongs to the kernel of D. So let us return to our example. If we have D in such way, D is equal to D sum of two partial derivations, then we have the following. D is equal to 2 partial derivation on U, and so V belongs to kernel of D. Then the maximal number of elements in one system of variables which belongs to D, of course, equal to 1, because I can't correspond system of variables such that both variable belongs to this kernel. And hence rank of D is equal to 1 again. Of course, these two definitions are equivalent because what variables from any system are in the kernel, such that these fi's are 0. So the number of variables which are in the kernel equals to number of zero summands in this sum. Okay. And why this characteristic is called rank? Because for linear derivations, I can correspond just an element, an nilpotent matrix. Let me take M is belongs to matrix n times n with constant coefficients, so just such that M in power n equals to 0 matrix. Of course, these metrics give us a locally nilpotent derivation if we apply it by d from x1 xn equals to m multiplied by x1 xn. One can check, let me say that it is an exercise, that rank of this matrix is equal to rank of this D. Okay. Now now the question is what rank can be, what rank can have a locally nilpotent derivation. First of all, let us consider the case, maybe let us start with the case n equals to 1, but this case is rather trivial. So if n equals to 1, then what is the form of each locally nilpotent derivation? each locally nilpotent derivation, we have just one variable x, and easy to see that d from x is equal to some constant. So our derivation is just this constant multiplied by partial derivation. And of course, we have that this derivation have, I'm sorry, okay. And then I have that these derivations have rank 1. All derivations have rank 1. Okay, easy, no, mostly easy, but non-trivial case is n equal to 2. Then there is a theorem that every locally nilpotent derivation in polynomial of polynomial ring in 2 variables can be diagonalized. So if we have d is locally nilpotent derivation of k of xy, then exist such coordinates u and v such that k of xy equals to k of uv, and our derivation have the following form. It is just f from u multiplied by partial derivation in u. What about the rank? Of course, there is a zero derivation which have rank 1, which have rank 0, but every other derivation in case n equals to 2 have rank 1.
Maybe there's f of v, not of u.
F of v, you're right. This is just a replica of partial derivation. Rank of d equals to 1. Okay. What about n bigger than 3? The right answer that rank d can be every number from 0 to n. But this is not a very easy task to obtain this derivation of rank n. Let us discuss what derivation do we know in polynomial on polynomial rings. If you think a little bit, you understand that every triangular derivation is locally nilpotent. What is triangular derivation? Triangle derivation is such, it has form f1, which is constant, multiplied by partial derivation in first variable plus f2 from x1 multiplied by partial derivation in the second variable plus fn minus 1 multiplied by partial derivation in n variable. I'm sorry, fn, which is from x1 xn minus 1. Just image of every variable is a polynomial in the previous variables. So, of course, this derivation is triangular because x1 goes to a constant, and in the first step it goes to 0. x2 goes to a polynomial in x1, and so on. What can we do? We can use this construction, triangular. We can use construction of replicas. If H belongs to kernel of D, then we can consider a derivation H multiplied by D. And if D is LND, locally nilpotent derivation, then H multiplied by D is also LND. The last one is just conjugation by an automorphism, and this is equivalent to changing of coordinates. If I have an automorphism of our polynomial ring, then I can consider conjugation of a locally nilpotent derivation by this automorphism, and this is also a locally nilpotent derivation. This is all possibilities for constructing LND in a naive way. But by this applying these constructions, you can't obtain LND of rank n. Let us prove this. Let us say that D is triangulable if it can be conjugated by an automorphism such that its image under this conjugation is triangular. Let me prove the following well-known lemma. That each triangular locally nilpotent derivation D have rank less than n. There is at least one variable which belongs to its kernel. Okay, the proof is as follows. We can consider polynomial ring in two variables. These two variables are such variables that x1 goes to a constant and x2 goes to a polynomial in x1. So this subring in B is invariant under our D. Then this D can be restricted to this subring. And this is an LND of this subring. It's easy to check that Leibniz rule is true for this restriction, and that image of every element under some iterations of D is equal to 0. Okay, then we have by this theorem, where it is? By this theorem, each locally nilpotent derivation in polynomial of polynomial ring in two variables have the following form. We have another system of variables u and v, such that they belongs to k of xy x2, and k of xy x2 equals to k of uv. And in this system of coordinates, we have that this restriction have the form f of v multiplied by partial derivation in u. But here we see that v belongs to kernel. We can to note that k of x1, x2, and so on, xn equals to k of uv, x3, and so on, xn. So v is a variable of all the ring B, and it is in the kernel of D. So it proves that rank of D less than n. So we have a variable in the kernel. Of course, we can construct a locally nilpotent derivation of every rank which less than n, just using nilpotent matrix of this rank. Of course, we can use just such matrix, zeros on the diagonal, zeros on the under diagonal, and some number of units upper the diagonal, then zeros and zeros here. And we can take R to be every number from 0 to n-1. Even for this derivation of rank less than n, one can ask, are they always triangular? And this is not true. one can construct a non-triangular derivation of some rank less than n. Let us say that most interesting for us case is n equals to 3. Of course, it is not most interesting, but this is just the case where we can prove something, because in general case, it's very difficult to prove something. Okay, and for this n equals to 3, we have one theorem which say that this case is better than general case. This is Mianishi theorem, and it asserts that kernel, let D be is an locally nilpotent derivation, such that for every locally nilpotent derivation, its kernel is isomorphic to algebra, polynomial algebra in two variables. Let me say that for n bigger than 4, for 5 and bigger numbers, there are locally nilpotent derivations with unfinitely generated kernels. And for n equals to 4, this is an open question if there are derivations with unfinitely generated kernels, but of course this theorem fails. Okay. Of course, when we go to replicas, then a derivation can be not can start to be not triangular, if even if the preimage was triangular. Let us consider the following best example. Best example, it was given by Bess. And this is very simple derivation, which is x goes to 0, y goes to x, and z goes to 2y. This example, of course, triangular, and we can compute its kernel. Its kernel is k of x and xz minus y squared. Okay, and we can take this element, let us denote it by sigma, and correspond the following derivation x, just sigma multiplied by x, sigma multiplied by d. I'm sorry. X goes to 0, y goes to sigma d, sigma x, and z goes to 2 sigma y. And this is the famous Nagata derivation. And well-known theorem of Shestakov and Umirbaev said that the corresponding automorphism exponent of this derivation is not tame, and of course it is not triangular, so this derivation is not triangular. It seems that what's a problem? Y goes to sigma x, but sigma contains z, and so this is not triangular in this coordinate, and this is not triangular in any coordinate.
Sorry, and in the Mianishi theorem, U and V, they are not coordinates, yes?
They may be not coordinates, just there are some U and V such that they generate the kernel.
Mm. And when we take a replica, it has the same rank, or
Yes, of
maybe
course. I try to say that when we consider a replica, then kernel does not change. So the number of variables which belongs to kernel is the same, and rank of this Nagata derivation also equals to 2.
yes,
Why it is not equal to 1? Because every locally nilpotent derivation of rank 1 have the following. I'm sorry, I should say it before. If rank of D is equal to 1, then we have n-1 variable in the kernel. x1, xn minus 1, they belong to the kernel. And then, of course, kernel is equal to this polynomial ring in this n-1 variable, because then transcendence degree should be n-1. And then we have only d of x1, xn. If it equals to f of x1, xn, and we have xn in this polynomial, then it can be checked that this LND, this is not LND, because we have degree corresponding to this D, which is a number of iterating of D such that we obtain, I'm sorry, deg D of H equals to M, where D in power M plus 1 from H is the first time that we have 0. And if we have this polynomial, we can consider it as null, as 0 from xn minus 1 plus so on plus sk from x1, xn minus 1, xn in power k. And then its degree should be k multiplied by degree of xn, so it's bigger or equal to degree of xn, so it cannot be locally nilpotent. And then we have d from xn is equal to f from x1 x n minus 1, and we say that d is equal to f from x1 xn minus 1 multiplied by partial derivation on xn. In particular, this d is triangular. So every locally nilpotent derivation of rank 1 is triangular, but for rank 2, there are some non-triangular examples. Okay, but before we can say a couple of words about rank 3 derivations in polynomial ring in 3 variables, we need some other assertions. So let us investigate the case of two commuting LNDs. If we have two LNDs, now we fix that B is K of K, Y, Z. So it's a polynomial ring in 3 variables. Okay. And let us consider two derivations, D and E. We say that these two derivations are equivalent if they have coinciding kernels. And let me assume that these two derivations, locally nilpotent derivations, they are not equivalent, and they commute. DE equals to ED. Then we can say that the following theorem, which was proved in Veronica's talk. That the intersection of these kernels is equal to polynomial ring in one variable, and this variable, this u, is a variable of this b. So it can be included in a system of variables of k, x, y, z. Just I shall not prove this theorem because Veronica has, but if you want an idea is rather simple, that when we have two derivations, then since they commute, then kernel of one derivation is invariant under the second derivation. And so this kernel is a polynomial ring in two variables, and this give a locally nilpotent derivation of this polynomial ring in two variables, and the kernel of this derivation is just polynomial ring in one variable. Of course, it does not prove that u is a variable of b, but this is true. And the first result, which seems to be our result, because we have not found it in any other papers, but it seems that it should be in some papers, but we haven't found it. Is the self-following theorem. Let us take D, locally nilpotent derivation of this B, and this is a criterion that D is triangulable. I'm sorry. Then D is triangulable. It means that it is triangular in some coordinates. If and only if there exists a commuting LND such that rank of this commuting LND is equal to 1. It's not a very difficult theorem, so let me prove this theorem. Proof is as follows. Firstly, let us assume that D is triangular. It is triangulable, but then we can change coordinates such that D is triangular. I know that B is polynomial in 3 variables, so D is just f from x multiplied by this plus f plus g of g of xy multiplied by v. I'm sorry, I skipped some assertion. Let D be triangular. Then we have coordinates x1, x2, x3 such that it is triangular. As in the previous theorem, we consider algebra K of x1, x2, which is invariant under this D. In this subalgebra, we can change coordinates such that this D should have x1, maybe new coordinate x in its kernel. Then let me take this coordinate x, the second coordinate y, and we understand that these two coordinates, so this is k of xy, and x is in the kernel, so it goes to 0. Y just belongs to this subring, and this subring is invariant under D. So y goes to f from x, and the last coordinate x3, which is equal to z, goes to some polynomial from these two variables, so to the g of xy. And now we just can take E equals to partial derivation of Z. It's easy to check that D and E commutes. Of course, rank of E equals to 1. How to check that E and D commutes? We just check that DE from X equals to ED from X, and so on from Y and from Z. Of course, from X, both are equals to 0 because E from X and D from X equals to 0. If we have DE from Y, it is equal to ED from Y, and it is 0 also because E from Y equals to 0, and D from Y is a polynomial in X, and E from this polynomial is equals to 0. And from Z also we have 0 because E from Z equals to 1, and D from 1 equals to 0, and D from Z equals to G from XY, and E from this G equals to 0. So they commute, and so we prove this theorem to one side. Another side, it's more complicated. Now let E be locally nilpotent derivation such that DE equals to ED, and rank of E equals to 1. Then we can assume that E in some coordinates equals to P of x y multiplied by the partial derivation. And then let us take this P, and we obtain that kernel of this E equals to K of xy. And this is D invariant. Then D can be restricted to this kernel. And this D is triangularizable in this kernel. And what we should consider, should consider DE from Z. From one side, this is equal to D from P. And from the other side, this is equal to ED from Z, because D and E commute. And now let us say that if this, what we should check that this belongs to K of xy. if we check this, then we have that D from Z belongs to K of xy, and in K of xy, this D is triangulazable. Then D is triangulazable in all B. So why it belongs to K of xy? Let us consider the power. Okay, let it be phi from x, y, z. Then let us consider the power, the degree, I'm sorry, deg d from phi. Okay. This is the degree or d from dp, and this is equal to degree d of p minus 1. From the other hand, how to compute degree d of this sorry, let me think a little bit. No. Okay. Let me say in other words, bad notations. I would say that phi is d from z. Then we consider degree by d from this. Before consider degree by d, let me just say that E, oh, sorry. E, E from phi, it equals to, since E is as follows, this partial derivation, it equals to partial derivation of phi by z multiplied by p. So E from phi, this is E from dz, this is d E from z, and this is d from p. And then we apply degree by d. Here, degree by d is equal to degree by d from p minus 1. And here, degree by d bigger or equal to degree by d from p, because we have multiplication of p and a polynomial. So degree of multiplication is bigger or equal to degree of one multiple. So this is a contradiction.
Sorry, Sergey, I didn't understand. How did you prove the triangle that this derivation d is triangular?
Okay, we understand that we have kernel of E.
Yes, and the restriction to this kernel is triangular. This is clear.
Okay, and the only one which we should check that d d from z belongs to d from z is equal to phi, and yes, there is some mistake. I shall check that phi belongs to k of u of xy.
Sorry
Yes,
to
it will be
interrupt.
nice. But you check that.
I think del phi by del z should be 0 from that contradiction.
Yes,
So
from this contradiction,
phi should be a polynomial in x and y.
if this is not 0, then we have a contradiction, because the degree of this one is bigger than degree of this one. The only possibility is that this guy is 0, and so we have not contradiction. Okay.
No, I don't understand this line. D of P equals D E of Z equals E D of Z, and this should belong to the polynomial ring in
Okay.
X and Y.
I just erased. That was a mistake. Sorry. D from E from Z is equal to P. So we have this line.
Yes. Okay.
Then we apply E from phi. From one side, this is this partial derivation multiplied by P.
Sure.
From other side, it equals to ED from Z, because phi is D from Z. And this is equal to, I'm sorry, it's equal to DE from Z, and it equals to D from P. And degree by D of this guy is degree of D of by P, degree of P by D minus 1. And this is greater or equal to P, degree of P, and this is smaller than
I see.
degree of P.
So the task is to prove that E of phi is 0, that it doesn't depend on that. Okay.
Yes,
Clear.
yes.
Mm-hmm.
Sorry for mistakes.
And the question, is this theorem true for arbitrary number of variables? Or you don't know, because this is specifically for 3 variables.
Of course, it's not true. I think that it is not true, because if we have an LND which commutes with LND of rank 1, then just n-1 variables then can be changed in every derivation which don't go from this. I'm sorry.
I see. Just take any non-triangular triangular LND on 3 variables and add 4th variables and take partial derivative.
Of course, it can be triangulable on 4 variable, and it's a difficult question. Maybe all non-triangular derivations in 3 variable become triangular when we add one more variable, but I don't know. But there is no reason to say that this theorem is true. I don't believe it.
Mm-hmm.
Okay, and now let us think about what we can say about rank one when we have commuting LND. Our task now, our local task, is to prove the following theorem. Let D be a locally nilpotent derivation of B as usual. Then there exists a derivation E such that it's locally nilpotent, and they commute. They are not equivalent. And they commute. If and only if there exists such H in B that it is local slice. It seems this means that D from H equals to F, which is not 0, but D from F is equal to 0. And this H is a polynomial in one variable. So there exists a variable U, which is a variable of B, such that that F is a polynomial in this variable. So let me say in simple words, there is a commuting locally nilpotent derivation, such if and only if there is an element such that its image in the kernel and its image is polynomial in one variables which belongs to the kernel.
Let me understand. So you take a locally nilpotent derivation D, and you consider two conditions on this derivation. The first one, there is a LND in the centralizer of D, which is not equivalent to D.
Yes.
And second condition, there is a polynomial in our algebra such that
it is local. It has degree 1.
It has degree 1 with respect to D. And
the image which belongs to this to the kernel. This is a polynomial in one variable.
So maybe it would be better to write that F belongs to K of U, because for now I'm reading that F is F of U something else.
Okay. Let me say
but
that.
it looks like a technical statement, not like a principal one, like a lemma.
No. It's a very I'm sorry. K from U. For example, okay, before the proof, let us discuss consequences. For example, if D is of rank 3, if rank D is 3, then there is no commuting LNDs.
You may write if and only if, right?
Oh, of course. Here, if and only. Because the proof of this consequence is very simple. If we have commuting LND, then we have such H and we have such F, and F is in the kernel and it is a polynomial in one variable. Since F of U, F is equal to F of U, and it belongs to the kernel, then U belongs to the kernel. Because this polynomial can be decomposed to the linear factors, And each linear factor belongs to the kernel because kernel is how to say it in English, factorially closed. And when f minus lambda belongs to this d, then u belongs to this. Then u belongs to this d. And then d cannot be of rank 3. Okay. And this is, in my mind, this is a of course, I would like to state an assertion in other direction, and it should be a way to prove that rank of D is equal to 3. If we have not any LNDs which commutes. Okay, what shall I do? I shall prove the theorem. To prove the theorem, I'll try to consider new subalgebra. Let H be a local slice of a derivation D. Then we can consider its kernel, let it be A. And the image of this local slice, D from F, or D from H equals to F. Then a well-known theorem that localization of B by F is equal to localization of A from H by F. So since A is a polynomial ring in 2 variables, it is K of UV. We can obtain a new subalgebra C, which is equals to A from H, which is a subalgebra of B. Okay. Moreover, when we deal with polynomial ring in 3 variables, then every locally nilpotent derivation have a unique up to equivalence minimal local slice. It means that this F, the image of this H, generates the Plin's ideal. Plin's ideal, this is an ideal which generated by image of D intersects by kernel of D by this A. And this is an ideal in A. So this H in some sense unique when F generates this Plin's ideal. This Plin's ideal is always principal for derivations in 3 variables. And then this, it is unique, says that this subalgebra is unique. So this subalgebra C can be in one way, it is a canonical subalgebra constructed by this D on this B. Now let us
I'm sorry, I just got a question about the theorem of the formulation.
Okay.
Is it the second condition equivalent to the existence of a variable in the Prince ideal of D?
No, Plinth ideal is generated by this F, and maybe this F is not coincide with U.
Excuse me, but
There is
I mean that U is in the kernel, but not necessarily in the.
in the Plinth ideal there is a
image.
univariable polynomial in one variable.
Okay, thank you.
Okay, I'm sorry. Let me restrict D to this C. What can we say? This restriction should be, let us note it by delta. Then delta from U equals to delta from V is equal to 0. And delta from H is F, which belongs to K of UV. So now we considered from the data B and the local and nilpotent derivation D from on this B. We construct a subalgebra C, which is isomorphic to polynomial ring in 3 variables. It is K of UVH, such that restriction of this D to this C is just F multiplied by partial derivation. Okay. Now, sorry, what should I say? Okay. Let us prove our theorem. Suppose there exists such E that it commutes with D. Then what about kernel of E intersect kernel of D? As we said, it is K of U for some variable U. U is a variable of B.
Sergey, a short question. Usually we have maximal 1 hour and a half, so there is still 5 minutes. What do you plan?
I'm sorry. Yes, it is very uncomfortable questions for me.
You may continue next time, so we may plan 2 talks.
If it's possible, I'm very sorry for this awful situation today. Maybe I should give proof of this theorem, and I continue next time. Is it possible?
Okay, let us do like this.
I'm very sorry. Okay, I try to maybe not 5, but 10, at least 15 minutes, and I'll prove this criterion. Okay, intersection of this kernel is polynomial ring in 1 variable. Then we can consider D restricted to the kernel of E. This restriction is a local and nilpotent derivation, and we know that kernel of E is isomorphic to polynomial ring in 2 variables, but there is a variable of B, which belongs to this kernel. So it can be included in variables of E. So this is K of UV. Okay, and U, of course, it belongs to the intersection of these kernels. U belongs to kernel of this restriction. Okay, since U belongs to this kernel, we say that this restriction, this is just a locally nilpotent derivation in this polynomial ring in two variable, and U is in the kernel. So this restriction just partial derivation which is f of U divided multiplied by partial derivation in V. Okay, and then we say that f of U belongs to this image. And f of U is a polynomial in one variable, which is a variable of B. And this prove our assertion to one direction. From the other side, now we say that image of D contains a polynomial in one variable, and we should construct this commuting locally nilpotent derivation. We say that let us take our local slice such H, such that D from H is equals to F. And let us consider E is a Jacobian derivation. This is Jacobian of U, H, and the argument. It means that E from any polynomial T is equal to I'm sorry, I should say in what coordinates this Jacobian matrix. I like to include this U, since U is a variable, then our B is equal to K of UVW. This is just the set of generators. And this Jacobian matrix we corresponding with respect to this coordinate. So here should be du by du, du by dv, which is 0. Let me say that this is 1, 0, 0. Here d h by du, dh by dv, dh by dw, dt by du, dt by dv, and dt by dw. And determinant of this. Okay, we can just have more precise formula that E is dh by dv multiplied by partial derivation in w minus dh by dw multiplied by partial derivation in v. Okay, this is our E, and we should check that this E is a good E. So what should we check? That it commutes with D, that it is not equivalent to this D, and nothing more. E is not equivalent to this D because E, I'm sorry, and that E is locally nilpotent. Jacobian derivation always a derivation, but not always locally nilpotent. So we should check that E is locally nilpotent. The most simple thing is that E is not equivalent to D, because these two guys, U and H, belongs to the kernel of E, but H does not belong to the kernel of D. So kernels are different. E of H equals to 0, but D of H does not equals to 0. Hence, E is not equivalent to D. Now we should check that E is locally nilpotent.
Not equivalent in the previous slide.
Previous slide.
No, in the previous line, not equivalent.
What?
I'm sorry.
Okay. We know that kernel of D is isomorphic to polynomial ring in two variables. Moreover, this U belongs to the kernel, because f of U belongs to the kernel. And so U belongs to the kernel. And so we can say that kernel of D is equal to a polynomial ring in two variables, U and something more, I don't know, P. Then it's a well-known theorem that D is proportional by some coefficient which is from this kernel to the Jacobian derivation given by U and P. And I can rewrite it as follows: S multiplied by dP divided by dV multiplied by dW, I'm sorry, dW minus dP divided by dW multiplied by partial derivation in V. Let me give here the formula of E. E is equal to dH dV minus dH dW dV. And now let us consider D from H. From one side, it is F by definition. From the other side, I can state H here, and I have S multiplied by okay, dP dV multiplied by dH dW minus dP dV dW multiplied by dH dV. And when I put P here, I have the same with minus. So this is minus S multiplied by E of P. Therefore, S divided F, divides F. But F is F of U. Hence, S is a polynomial in one variable U. Now, let us say that E squared by P is equal to one more computation. S of U multiplied by E of P is equal to minus F, F of U, and hence E square of P is equal to 0. Now let us say that if I correspond K of U, P, H, this is just A from H, and this is our C. Then here we obtain that E from U is equal to 0. E from E from P is also 0 because E from H is also 0 because it is Jacobian derivation with H. And E square from P is equal to 0. And what about elements of B? We said that B localized by F is equal to this A of H localized by F, so to C localized by F. So every element B from B have the following form. This is just a polynomial in U, P, H divided by some power of F. And hence, this locally nilpotent derivation E, it from F equals to 0. And since it's locally nilpotent on this C, so some power of U, E from U equals to 0, E from H equals to 0, E square from P equals to 0. Hence, this F goes to 0 in some iteration by E. This F just a constant with respect to this E. So E in some power K from B is equal to 0. Hence, E is locally nilpotent. We can even consider E as local nilpotent derivation of this algebra, but B should be, of course, invariant because by definition E is a derivation of this B. And the last thing which we should prove is that ED equals to DE. And the idea is the same. We should prove that this is true for U, for P, and for H. And since every element have this form, then and D from F equals to E from F equals to 0, so it's enough. And it's just a simple computation. D from U equals to E from U equals 0, and so on. Let me say that ED from H equals to E from F equals to 0, and DE from H equals to 0 because E from H equals to 0. And the last thing is DE from P equals to this. Let us multiply it. It's more convenient to multiply it by S, DE from P. Then it is D from S, because S is polynomial of U. And this is because S multiplied by, here it is, S multiplied by E from P is equal to minus U. So this is D from minus F of U, and this is 0. Hence, DE from P is equal to 0, because S is not, and ED from P equals to 0 because P is in the kernel of D. So we just proved that ED equals to DE. The main idea that we don't have deal with this algebra B, but we deal with this algebra C. And it's more convenient because we know how to deal with its generators. So this theorem is proven. And if it's possible, I'll be happy to have better talk in the next time.
Okay, but let us fix for future that we can have extra 5 minutes, but not more, not 15 minutes.
I'm very sorry.
And it is okay to have some time for discussion, for questions, and so on. So don't give so much technical details in extra 15 minutes. But let me try to summarize. What did we prove today? Firstly, we have polynomials in 3 variables, and a local nilpotent derivation is triangular if and only if its centralizer contains an LND of rank 1, right?
Yes.
Second result, which you prove this last part. This is the centralizer of an LND contains a non-equivalent to the original one LND, if and only if you have some technical condition. But this follows from this technical condition that if you have an LND of rank 3, then its centralizer contains only LNDs which are equivalent to this LND, right?
Yes.
Is the converse true? So
the converse is true for irreducible derivation. If we have an irreducible derivation, then if it have not commuting local nilpotent derivation, then it is of rank 3. And our plan to the next time is to find some examples of such irreducible derivation which have not commuting ones, and therefore they are of rank 3.
So you will prove that this equivalence holds in both directions, and then you will apply it to construct an explicit example of LNDs of rank 3, right?
Not exactly in both directions, but for a reducible, yes. Yes, for a reducible, yes.
So one of our aims, and at least for me, this is very interesting, to give explicit example of LND of rank 3, right? So we will have it.
Yes, we will have it. To be honest, there is one in book of Freudenberg, and I will prove the same derivation that it is of rank 3. But in Freudenberg, there is a mysterious technique, and we prove it more easy, and we can iterate this example, so we can construct some more examples which are, of course, similar to this, but they are other.
And we will have complete proofs that this is an LND of rank 3. We don't use black box like theorem of Shostakov and Umirbayev. It will be given here by explicit arguments, right?
Yes, so we use Mainichi theorem, something what I have used already, but nothing more.
Mm-hmm. Okay, but Mainichi theorem, this is a deep and difficult theorem, I see. Mm-hmm. Okay, dear colleagues, are there any questions, comments? If not, then let us wait for next Sergey talk. We will discuss when we should have it.